there were many more talks on reductive groups and parabolic induction, and the Shivprakash ran this tutorial talking about Cuspidal representation. So I guess today many more people are much more familiar with theory of reductive groups and some theory of representations. So G reductive group, E parabolic subgroup, and one writes P as M times N, and this is called the Levy decomposition, where N is a normal unipotent subgroup, where M is a reductive subgroup of E, and N is a normal unipotent subgroup. All these things are GFQ, but once in a while I will emphasize FQ, but sometimes I will not, just to shorten the notation. But there is always a finite field under consideration, and this P is PFQ, and so on. And the fact that this is a normal subgroup means that there is a mapping from P to M, which kernel is N. And parabolic induction consists in taking a representation of M treated as a representation of P, via this mapping from P to M, and then inducing. Induction from P to G of this. So this is called parabolic induction. I mean, one emphasizes the fact that this induction is not some simple induction. A simple induction is given a representation of a subgroup you induce. This is also similar, but the induction is of a certain kind of representation of the parabolic. Parabolic may have many representations, but we are looking at those representations of the parabolic which factor through M, meaning on N they are trivial. So this is a special kind of induction called parabolic induction, and okay, so this is one definition. And then one defined cuspidal representations phi of G are those for which pi n is 0 for all P not equal to G, a parabolic subgroup. So these are called the cuspidal representation, and these are supposed to be, so cuspidals are supposed to be building blocks of all. Cuspidal are supposed to be building blocks of all representations. And this was made precise in the following theorem, which is in some ways it has the status of a theorem, but it's only an elementary lemma. So it's nothing non-obvious that G reductive, let's say, by any irreducible representation of G, then there exists a parabolic P, parabolic P, and an irreducible representation and irreducible Cuspidal representation W of M, such that pi is contained in this parabolic induction. So this is maybe part A, and it was also mentioned last time that this data of M comma W is unique up to conjugation. So to any representation, there is a Cuspidal data which is associated. So to any representation, there is this W is a Cuspidal representation of a levy, and this data is unique. So there is one of the subtleties in the subject is that two non-conjugate parabolics may have conjugate levy subgroups, but somehow this doesn't affect the subject too much. Anyway, that is a bit of a subtle point, and I don't want to elaborate on that. So, remark. I mean, this is a bit of a subtle remark that two parabolics P1 equals m times n1 and P2 equals m times n2 may be non-conjugate. But it doesn't matter. It does not matter in the sense that the parabolic induction with respect to P1 or P2 is the same. But that requires arguments, somewhat non-obvious arguments. Okay, so therefore, maybe I did not quite say this. So maybe let's continue with the same kind of a theorem. Let M comma W be a Cuspidal data, which means that this is a levy subgroup and W is a Cuspidal representation of the levy. And then one is looking at induction from P to G of this W. And you know, I have said that something is a submodule of something else. Whether that's a useful information or useless information. You know, any representation is submodule of some other module. It doesn't help to understand the representation so much. Any representation, for instance, is a submodule of the regular module, but it says almost nothing about the representation. So in some sense, such a theorem would be useful. I mean, okay, this has some utility, everything has some utility. This will have some utility if somehow there are not too many sub-representations. And more precisely, if you can understand all submodules and their multiplicities. So indeed, so part A of the theorem says that V is irreducible if and only if W has M comma W has no non-trivial automorphism. Okay, is not stabilized, is not stabilized by any non-trivial conjugation in G, i.e., if n belongs to G, conjugates M to M and takes W to W, then N must belong to M. So this is the theorem which is analogous to what I stated for GL2 of a principal series, that a principal series alpha beta, so maybe Remark, I said that the principal series alpha beta is irreducible if and only if alpha beta is not equal to beta alpha. And this one is a more general form of the same theorem, and it's proved also by the same method as that is proved. So the statement is, I hope, clear that you have inner conjugation by n, which must take M to M, and once it's an automorphism from M to M, it makes sense to say that a particular representation of M is left invariant by that automorphism. And one is just saying that there are no such non-trivial automorphisms. Any conjugation within M has certainly that property, and that's the only one. And part B is a slightly more precise version of this. You know, one way to understand that a representation is irreducible or not is to calculate its endomorphism ring. A representation is irreducible if and only if its endomorphism ring is one-dimensional. Always scalar multiplication is an endomorphism for any module, and if that is the only endomorphism, then the module is irreducible. And this one says that at least as a vector space, it is same thing as W M. So I'm using maybe W for too much. So let's call it WS, where WS is the subgroup of the while group, which stabilizes. So I must apologize for a little incorrect notation, which I don't want to change for the moment. I have used W for a representation, and I'm also using W for the while group. And this is the subgroup of the while group, which stabilizes M comma W. So, you know, in this theorem, maybe this was any arbitrary element of the group G, which normalizes M and which takes W to W. And this one says more precisely that you need not look at all elements of G, but that's a general elementary structure theory, but only those elements which are in the while group. And the way this definition is made, it is a subgroup, and each element of Ws gives rise to an endomorphism, and as vector spaces, these are isomorphic. And eventually, the theorem is that even as rings, they are isomorphic. So the isomorphism is both as a vector space and as a ring. Although the fact that it is isomorphism as a ring is a much more subtler theorem, and it is also not true in all cases. So it is, I have the feeling that it is true if the group has connected center, but it may fail in a few cases. But isomorphism as vector spaces is certainly true, and but as rings, maybe not always. All right, so there is a particular case of this theorem which is prototypical of how things need to be understood. And so, a special case of the theorem. This theorem is when E equals M times N is equal to B is equal to T times G. So instead of looking at general parabolic, one looks at the Borel subgroup. And this is the Levy decomposition for the Borel, meaning Borel is torus times the unipotent radical. And in this case, one looks at induction from B to G of the trivial. So trivial representation, of course, is stabilized by all elements in the while group, and therefore its endomorphism ring is isomorphic to CW. And this is an isomorphism of rings. This is an isomorphism of rings for all G. So I was saying that, you know, that theorem about isomorphic to CWS is not true for all groups. It's true for almost all groups. I have the feeling that it does go wrong in some cases if the group has a disconnected center. But I don't want to worry about that aspect too much, but in any case, this is true for all groups. And once you know endomorphism ring of a certain module is isomorphic to this is of course a regular representation of the while group, and therefore, therefore it says that endomorphism induction from G to this is given by summation of let's say V rho tensor induction from B to G. So where rho belongs to W check, and these are irreducible representations of the while group. V rho are irreducible representation of the while group, and this is, so to say, the rho isotypic component of this part, and they appear with multiplicity as much as dimension of V rho. So such that so if you induce the trivial representation of the Borel to the group G, then you get as many irreducible representation as there are that of the while group, and each one appears with multiplicity, which is the dimension of V rho. Is the theorem looking okay? But yeah, so this one says that you understand the representation in some ways. I mean, in my mind, you still have some work to do to take out these components. And I do not quite know how that is done. But presumably that is something doable. Just to give you an example, induction from B to GL2 of 1 is equal to 1 plus a representation which is called Steinberg. This is a representation of dimension Q that I talked about, and then Shivprakash gave more details on this one. And if you did something similar, induction from B to GL3 of 1, then this will be 1 plus 2 times pi plus Steinberg, which corresponds to the fact that C of S3, as you all very well know, it is 1 plus sine plus 2 times. So the group ring of symmetric group has dimension 6, and this is 1 plus 1, 4, and this is 2 times 2-dimensional 4, 6. And corresponding to this representation, there is this 2, and it's good to do this dimension count. The dimension is given by 1 plus p cube plus 2 times p square plus p, and which is same thing as it's supposed to be order of GL3 upon order of B. And this order of GL3 is Q cube into Q cube minus 1, Q cube minus Q, Q cube minus Q square upon Q cube, Q minus 1 cube. I hope it, so okay, there is a P and there is a Q, but I hope it will work out. Sorry? This goes away, and this has degree 9, this has degree 3, 6. There is something wrong which I am. Right. So there is, So I have to also take out the Q part. So Q cube, and that would have given me Q cube minus 1, Q square minus 1, Q minus 1 upon Q minus 1 cube, which is Q plus 1 into Q square plus Q plus 1, and voila. that's there. Good. Sorry? You know, I am saying that the endomorphism ring is isomorphic to CW. If you think about what that means, is that if you write it as a direct sum of irreducible representation, isotypic component, then this gives rise to V rho tensor V rho check, and this is CW. So this isomorphism implies this for CW is this. You know, this is supposed to be a G module, but you know, in some sense, what one is saying is that this representation is simultaneously a representation of G and W which commute. It's equivalent to saying that there is a simultaneous commuting action of G cross W, and as a module for G cross W, it has this decomposition. So this is G module, this is the while group module, and it's a direct sum with multiplicity 1. Yeah, sorry, I made a little mess of it here, but it's good to struggle a little bit. This is supposed to be Howlett-Lehrer theorem. Yeah, this is Howlett-Lehrer theorem. Sorry? They do the all algebraic groups also. Algebraic groups mean reductive groups. Yes, reductive groups. Yeah. And as I said, that it's not fully true, but that is not something which I am letting out. There are many subtleties in the subject, and one of the subtleties is that if the center is disconnected, then something goes a little wrong. It takes a lot of effort of many people to fix that problem. But eventually it is roughly that. Okay. Yeah, maybe Frank can, perhaps I'm sure he can correct me later, but maybe it's not relevant for the moment. So far, good? So the point I'm making is that this is the simplest kind of principal series, and it gives rise to many representations. And somehow, in some sense, this is the simplest representation, but one of the things to be done is to understand these components in a more precise way. And I am saying that that's not a trivial problem. Because this isomorphism is somewhat abstract. All right, so I think at this point, just to continue with this theme which is there on the board, you know, the Steinberg representation has been maybe not formally introduced, and that plays an important role in the subject. And maybe I want to introduce the Steinberg representation. So this is indeed a very distinguished representation which makes its appearance in a lot of representation theory. And its definition is given, so Steinberg of G is defined to be summation from -1 to the power rank of P, induction from P to G of the trivial representation. Here P contains a given B, and Rp is number of positive simple roots which for which. So maybe in some pictorial sense, parabolic looks like this, and for this parabolic, you know, there are roots which are contained here, which also have a negative. Roots here have negative, but this root has no negative. So here one is just interested in number of positive simple roots alpha, for which minus alpha belongs to P. So in particular for the Borel, it's an empty set, and therefore this is 0, and -1 to the power 0 is 1. So it starts with induction of, so therefore this one looks like induction from B to G of trivial minus induction, so to say, of P1 to G of trivial. But these are, so to say, next smallest parabolic plus, then plus sign, P2, then minus, and so on. So this is what is called inclusion-exclusion principle. Inclusion-exclusion. So you look at functions on G mod B, then you take out those functions which are left invariant by P1. This is the next minimal parabolic, then this is the larger parabolic, then still larger, and so on. And each time you change the signs. So this is the Steinberg representation, which is defined for all groups. And so theorem that Steinberg of G is an irreducible representation of dimension equals Q to the power which is also also maximal power of Q dividing G of Q. You have to do all parabolics which contain a given Borel, and the way it is defined, you look at all functions on G mod B minus functions on G mod P1, where P1 is the next larger parabolic, plus P1, P2, which is the next larger parabolic. So it's an alternating sum. And as I said, there is this thing called inclusion-exclusion principle, which is what is behind that expression. If for the case of GL2, it will be this induction minus the next parabolic will be G, and it will be induction from B to G of 1 minus 1. So it is just that expression. And then for GL3 already there will be another term, and it's this alternating sum, which is the full object, and that 2 pi can then be defined in terms of these modules. Yeah. So Steinberg is one of the simplest of the components which one understands very well. And there is this theorem. And one of the really marvelous properties of the Steinberg is that the character of the Steinberg of G on G is equal to non-zero if and only if G is semi-simple, i.e. order of G is co-prime to QP. And more precisely, character of the Steinberg of G at now. So semi-simple element are those elements which are diagonalizable. So they belong to the diagonal, and by definition, the diagonal elements belong to FQ bar star. So they have orders which are co-prime to Q. And any element can be triangulated, and the Jordan decomposition. And if there is a unipotent part, then it will carry some unipotent element whose order is a multiple of Q. So therefore, this statement that these are equivalent or is an elementary fact. And once it is semi-simple, it can be put inside a torus. Okay, so the order of theta g, this is given by a certain signs which are very important in the subject. Sine of gs naught times order of gs naught p part. So I will define these terms. They are somehow one of the very important signs which come up in the subject. Ws is the subgroup of W which stabilizes the pair M comma W. It's by definition, it is the stabilizer. It is the stabilizer. So what happens is that those elements of W which preserve M and also preserve W. It is largest, or you may just say stabilizer of this pair. So you can say that elements W permute these objects M comma W, and stabilizer of this particular pair up to isomorphism is what is Ws, stabilizer. Which means that it's first of all fixing M. It's fixing M, and I mean there is a little bit of notation to keep track of, that you have fixed a maximal split torus somewhere, and M is supposed to be that particular levy. So somehow the while group conjugates the levy subgroups, and you are looking at which of those elements fix that levy and the representation. All right, so I was talking about these signs, which, as I said, is very much present in character theory, that characters, I mean, somehow, if one wanted to know character up to sign, things are always much easier. There is always a plus minus one sign, which is a lot of subtlety. A lot of subtlety, but luckily this one is not one of those difficult things to define, but as I said, this organizes a lot of character formula. So where epsilon G, so for any reductive group G, connected reductive group, this is defined, and therefore once I define that, then it's also defined here, and this is okay. So this is equal to -1 to the power split rank of G. So, I mean, I cannot do too much to define for you what is a split rank, but you know, a group has many tori, but there is one particular torus which is simplest, which is as split as it could be. So, for instance, for the group GLN, this contains FQ star to the power n. And therefore, the split rank of GLN is n. So typically, split rank of the group, yeah, these groups are also called split because they have as large split groups or as possible. So the maximally split, and then this torus contains, is equal to, so to say, T anisotropic times T split, and it is dimension of TD that one is talking about is equal to split rank of G. So just to give you a few examples, so for GLN, so GLN rank, split rank is equal to n. For SLN, rank is equal to n-1. For SP2N, the rank is equal to n. And for SO2N, the rank could be either n or n-1. So this is one of those little more complicated group. And for UN, the rank is supposed to be integral part of n by 2. So this sign epsilon g is there, then epsilon of g naught s is there, and there is this very beautiful convention in the subject that for any number n, one writes it as n times np times np prime. So one writes this into product of primes, and these are p powers and the rest, p component and p prime component. And that is that. So what that means is that the character of the Steinberg is powers of p up to a sign. So let me just regions of signs. GS has not been made, right? So GS is supposed to be the centralizer of S, where GS is centralizer of S in G, of S in G, and GS naught is connected component of identity, and which is a reductive group. Yeah, so presence of science in character theory. So just to remember this, we said that the character table of GL2, I said a few words and then Shiv Prakash elaborated on this. So there is the discrete, there is the principal series chi, and there is the discrete series chi, and then there are these elements, split elements, and to use the notation of Frank, let's say that these are the non-split elements. So the character value of principal series at this element is chi x plus chi x w. It is supposed to be the sum of these two. And here it is supposed to be 0, and here it is supposed to be 0, and here it is so the point I'm making is that this comes with a positive sign, this comes with a negative sign, and then maybe one might as well do this other element 1, 1, 0, 1, u, and the principal series has value 1 here and minus 1 there. Character table is very rigid, I mean, each and every number is rigid. You cannot tamper with the sign and hope that you will get the end correct result. So there are lots of signs, and Steinberg carries some of the signs nicely. We have 4 minutes, so I will, today I will not take more time. Main theorem of the linguistic was conjectured by MacDonald. And who made the following conjecture? So G reductive, T a maximal torus. Then there exist representations RT G theta for all theta So this T, just to be sure, this is TFQ, but I am talking about G as GFQ T, so this is such that it is non-zero only on those semi-simple elements which can be conjugated to T to TFQ in GFQ, and their values on unipotent elements, values on unipotent elements is independent of theta, and the character value or E, G, theta, its value at the element S. So this was supposed to be a representation or equivalently the character, and its value at S is given by epsilon G naught S times maybe order of G. So yeah, this is something I didn't want to. 1 upon GS naught. This is FQ rational points, and this is the P component. This is T, torus T, and then there is a summation of theta of G inverse SG, where this summation is over G belongs to GFQ, such that, yeah, so this was known as McDonald's conjecture. It suggests that there are representations for general reductive groups which have the same general feature as this formula, except for a few of those numbers which are maybe not so difficult to guess by looking at a few cases. He suggested that there are representations, they need not be always irreducible. We will come back to that tomorrow. And on semi-simple element, the character theory is very elementary. He did not make a conjecture about what the values should be on unipotent elements. And anyway, as far as I'm concerned, there is no simple answer. It is independent of theta, so somehow it's some kind of a universal constant. So I think it was also mentioned in various talks yesterday and tutorial that the set of tori is a simple object. It's basically conjugacy classes in the while group. So there is conjugacy classes in while group which determines the torus, and then the set of unipotent elements is also related to somehow partisans or conjugacy classes, and for the pair T and unipotent, there is some thing called Green's function, which determines the value at those unipotent elements. But anyway, I don't think I will have much to say about unipotent elements. Thank you.